So understand that the corresponding polynomial approximation for a function, notice this approximates the function, no matter how many terms that we have. Because n is a finite number, no matter how many terms we have, it's still going to be a function approximation. So I just wanted to point that out before we move on. So let's get to some examples. This says find p sub 7, Taylor polynomials for f of x equals sine of x. Based near x equals 0, plot everything on one set of axes. So here, a equals 0. So everywhere that there is an a in that formula that we just wrote down, we're going to put a 0. We're going to start with p sub 1. Then we'll add to it and find p sub 2, and we'll keep going all the way down the line until we get to p sub 7. Because remember, the next polynomial is just the prior polynomial plus the next term. So we're going to go back to our formula and write our formula down. We have p sub n of x is f of a plus f prime at a times x minus a plus the second derivative at a over 2 factorial, or 2, but it's easier just to keep up with the factorials, plus the third derivative at a over 3 factorial times x minus a cubed, plus the fourth factorial evaluated at a over 4 factorial. See how easy it is to keep up with this formula? The fifth derivative evaluated at the point of tangency over the fifth factorial, x minus a to the fifth, sixth factorial evaluated at a over 6 factorial, x minus a to the sixth. And if we're going to stop at n equals 7, we would say p sub 7 includes the seventh factorial, or sorry, seventh derivative evaluated at a over 7 factorial times x minus a to the seventh. So that's what we're after. So the first thing that we're going to do is we're going to find the output of the function and all of our derivatives. That's the first thing we're going to do. Then we're going to evaluate all of our derivatives at our point of tangency. So then it's just a matter of plugging in all those values. So we have f of x, our function, is sine of x. So the first thing I'll go about doing is finding the first 7 derivatives in x. Now remember, every time I show you an example, I am modeling exactly what your work needs to look like on homework, on quizzes, on exams, and ultimately on the BC. As an AP reader, I know what they're looking for. We want our work to be clear, succinct. So if our function f of x is sine of x, the first derivative is positive cosine. The second derivative is negative sine. The third derivative is negative cosine. The fourth derivative is positive sine. And now we're back in our loop. The fifth derivative at x is positive cosine. The sixth derivative at x is negative sine. And finally, the seventh derivative at x is negative cosine. So there are all of our derivatives. Now the next thing that we're going to do, and give myself a little extra room, is I'm going to evaluate all those derivatives at our point of tangency. So I need f of 0, I need f prime at 0, f double prime at 0, f triple prime at 0. And notice I am showing the AP reader all of this work. They don't have to guess where my work came from. It's all right here on the page for them. I showed them the first 7 derivatives in x. Now I'm going to show them evaluating those derivatives at 0. The sine of 0 is 0. The output of the function at 0 is 0. So p sub 1 of x will not have f of a in it. F of a has a value of 0. Cosine of 0 is positive 1. Negative sine of 0, 0. Negative cosine of 0, negative 1. Or sine of 0, 0. Cosine of 0, 1. Negative sine of 0, 0. Negative cosine, negative 1. So there we are. So now I'm going to write my 7th degree, p sub 7, my 7th degree Taylor polynomial. I'll come back up here. P sub 7 of x is the output of the function at the point of tangency, that's 0, so I'm not going to write it down, plus f prime of a, which is 1, times x minus a, or I could just as easily write x. The second degree term has a coefficient of 0. I'm not going to show it. The third degree term, which remember is the third derivative at a over 3 factorial times x minus a cubed, where a is 0. So the third derivative at 0 is negative 1 over 3 factorial times x minus a cubed. You might see me write that as x cubed over 3 factorial. The coefficient to the 4th degree term is 0. I'm not going to show it. The 5th degree term has a coefficient of 1, positive 1, over 5 factorial times x minus 0 to the 5th. You might see me write that as x to the 5th over 5 factorial. The 6th degree term has a coefficient of 0. It's not going to show up there. And the final, or 7th degree term, has a coefficient of negative 1, and that's over 7 factorial times x to the 7th. So minus x to the 7th over 7 factorial. That is p sub 7 of x. So it looks like a lot of work, but as you can see in practice, it's not. Building these polynomials, and here we built one to the 7th degree. It has to do with, number 1, yes, knowing your derivatives, and number 2, remembering that you have to put that derivative, you have to evaluate the derivative at the point of tangency a, and you have to put it over the factorial of the degree of your term, and then multiply that by the linear factor raised to whatever degree belongs in that term. So you see how important knowing that formula is. Well, here they are. Here are all of the polynomials. The function is this blue function. Here is f of x. Here's the sine function. The pink function, the linear function here, is p sub 1. You can see that very near our point of tangency, that our line and our function behave the same. But the further away we get from x equals 0, which is our point of tangency, the less and less and less the line acts like the sine function. So let's look at the green function. The green function is the cubic function. Here's p sub 3. Remember, p sub 2 doesn't show up because it had a coefficient. The 2nd degree term had a coefficient of 0. In other words, there is no parabola, there is no quadratic function that's going to behave like the sine function near x equals 0. So we jump right to the 3rd degree function, or the cubic function. That's the green function. Look how much further away the green function gets us, the cubic function, than the linear function does. That green function, further and further away from 0, acts like the sine function. Again, we don't have a 4th degree function. The purple function, which is this function here, the quintic function, here's p sub 5, and here it is up here, p sub 5. it acts like the sine function even further away than the first or third degree approximating polynomial does. We get next to no error, a distance of almost 2 full units in the plane to the right and to the left of our target point, our point of tangency, x equals 0. That's pretty good. Now this last one right here, here's p sub 7. There it is there, and here it is here, p sub 7. And p sub 7 gets us even further away from that center point around which we built these approximating polynomials. So do you see that forcing the polynomial to have the same slope, forcing the polynomial to have, in this case, not the same concavity, but the same attributes as the third derivative, and the same attributes as the fifth derivative, and the same attributes as the seventh derivative of sine, forces the polynomial to bend and twist and behave just that much more like our function the further and further and further away from that point of tangency that we get. Let's say we wanted to use a Taylor approximating polynomial built around x equals 0 to approximate the sine function at x equals 4. Well, at x equals 4, here's the output of the sine function. Here's the output of the 7th degree Taylor polynomial. It seems like to me if that is not an acceptable amount of error at x equals 4, error at x equals 4, then what we would need to do is to continue to add terms to this polynomial, terms up to degree n, whatever that might be, so that our error at x equals 4 was acceptable. So there's your first example of building a Taylor polynomial to a given function at a given point of tangency. Not difficult, but very important that you know that formula. So Taylor polynomials are the polynomials that we've been dealing with. They are built around any real number value x equal a. In the special case where a Taylor polynomial is built around x equals 0, it's given a different name. It's called a Maclaurin polynomial. Now, I've always been real good to tell you when you need to know names or theorems or whatever, you need to know both of those. You need to know that if you're asked to build the Maclaurin polynomial around a function, that they've already given you your point of tangency. By telling you they want the Maclaurin polynomial, they're telling you you're building around x equals 0. If they ask for a Taylor polynomial, they will always give you the value of a around which to build that polynomial. They will almost never give you the fact that a Maclaurin polynomial is built around x equals 0. You're supposed to know that. All right? So the example we just explored was a Maclaurin polynomial. We built it around x equals 0. So we're going to build another Maclaurin for now the cosine function. And now we want p sub 10. So we're going to have to find the first 10 derivatives of our function cosine of x. I'm not going to start on this example. I'm actually going to go on to another video, and we should be able to finish up the examples hopefully on a fourth and final video here. I know it's a lot of information, but I want to make sure you can build these polynomials and understand all the terminology, the order, the degree, Taylor, Maclaurin, all that. So look for another video, and we'll do this and some more examples so that you'll feel more comfortable with this.